Alright, so projectiles launched at angles. Please find this in your notes package. Okay, the key difference between this stuff and what we talked about on Friday is that the initial vertical velocity is not zero. You're going to be firing a projectile at an angle. And it's always like an angle up into the air, not towards the ground. So if you think about like a golf shot in golf, the ball goes up and then the ball goes down. But they have lots of different shots that they need to make in golf, because sometimes maybe they need to go over a tree, maybe they need to go under a tree, maybe they need to go around a tree. So there's all types of different launch angles that you can start with. And you could probably think about like, what's the video game with the birds flying? Angry Birds. Just, if you've ever played Angry Birds, just think about that game. What happens is you tug the bird back and then you set it at an angle. What happens if it's quite a low angle? It just shoots across, pretty much straight across the screen. But if you aim it up, it goes up and then it comes down. And that's, Angry Birds is exactly this. Like the programming for Angry Birds would be exactly based on this stuff. Okay? The reason they start you off with this bullet is because for what we did on Friday, the horizontal projectiles, that is true. So there's a key difference between these two ideas. Okay, the initial speed is at an angle and you have to resolve it into x and y components. So that's like the first step. So for this bullet, this is your first step, resolving the vector into its components. Okay. And then this bullet is the same as on Friday. Time was the one, same with the riverboat problems, time is the one variable that you can cross over dimensions. Like you can use time in the x, you could use time in the y, and it's the same time for both. So that's key right there. And vertical acceleration is always g, 9.81 meters per second squared down. And the vertical velocity at the highest point is 0. So ball goes up, ball goes down. At the very maximum height of the trajectory, the vertical velocity is 0, because it's traveling up and then it's traveling down. So it's positive vertical velocity and then it's negative vertical velocity. So somewhere in between it had to be 0. And that will be at the top. And the horizontal acceleration is always 0. So right here under this bullet, you can put Vx constant. Vx is constant. Okay, jot that down. Vx is constant. And what that tells you is that for the horizontal velocity, you're just using V equals d divided by t. For that last bullet, that guarantees that the horizontal component is uniform motion, and you don't have to use those kinematics equations on the horizontal motion. All right, let's take a look at some, yeah, horizontal velocity is the same. Let's take a look at the animations. Okay, somebody make a comment about the horizontal arrow. The horizontal arrow, somebody make a comment about it. On all three. Yeah, on all three animations, they stay the same. Somebody make a comment about the vertical velocity. It's changing, right? If the velocity is changing, it must be... If the velocity is changing, it must be accelerating. The acceleration always points down. So when the ball is on its way up, the acceleration works against that initial vertical velocity and it slows it down, right? And then eventually, after the maximum height, it will speed up in the down direction. Okay, and then the only other difference between these three animations is the angle upon which it's released. So, from in increasing order, a 30-degree launch angle, what do you notice about it compared to the 60-degree launch angle? It goes further? In which direction? Yeah, it goes further horizontally. That horizontal displacement has a special word. Does anybody recall? And it might screw you up with your math class, but we call the horizontal displacement the range. Okay? And the vertical displacement, if they ask you for that, most often they're asking for the max height. It doesn't have to be that though, but usually that's what they're asking for. Compare the 30-degree launch angle with the 60-degree launch angle. Which one goes higher? The 60-degree goes higher, right? But at what expense? You lose the distance horizontally. It should anyway. Yeah. If everything's otherwise the same. Okay, let's keep going. That you should be able to read. So maybe just give me 2 seconds. Okay, so treat each component x and y separately, think vertically and horizontally. And this picture, you have that picture in your book? Okay, that pretty much summarizes everything, okay? And maybe right on this page you can write the word symmetry. Like write the word symmetry for the y component. Like look at that y component. If you were to identify the exact same position on the other side symmetrically, like if you could draw a line down the middle and mirror reflect over to the other side, you would have perfect symmetry if you were in a best case scenario, like there's no wind, etc. Okay, so like this third x on the left and that third x on the right, see how the up arrow matches the down arrow in size? So it's the same size, it's just the opposite direction. So you need to make a quick highlight of that too. So write the word symmetry, symmetry, and then put same magnitude, opposite direction for vertical component. Okay? Same magnitude, opposite direction for the vertical component. Symmetry. Because that fact is actually going to, in a nice, clever little way, help us with our formula and solve for some missing variables. So, speaking of symmetry, with this animation, it will be symmetric to there. After that, it's not. Because you can only be symmetric upon where you shoot from and where you land. So after that, it's no longer symmetrical. So for this slide, what you might want to do is draw a horizontal line. I'll use my meter stick from where it's launched from. So I would draw a horizontal line like this across the cliff like this. And then as soon as the ball or the projectile is on the other side of the ruler, you know, below the cliff's edge, you lose that symmetry. It's now going beyond where it was launched from, and it's going to accelerate to speeds that it never had going up. So if the maximum speed is the launch angle, the initial velocity is the maximum speed, it will be going, the projectile will be going faster than what it was launched after it goes past the cliff. And you can see it starts at 60, goes down to 60, and then goes beyond 60. So watch the Vy. The Vy starts at 60, reaches 0 at the top, minus 60 when it's level, and then beyond minus 60 when it's below. Okay? As time goes on, velocity changes. It's dependent upon the acceleration, which is 9.81. Notice the horizontal velocity remains unchanged. All right. All right, let's do this. So you have a football being thrown at a 15-degree angle. That angle's always going to be made with the x-axis, so it's a 15-degree angle of elevation from the x-axis. So you can always draw it that way. And the speed that they give you is always the resultant speed. It's the hypotenuse vector. So what you can do is just draw that right away. Okay, so if this is 18 meters per second, that's your velocity vector. What you can do, you guys shouldn't be on your cell phones right now. What you can do is just break it into your Vx and Vy right away. You can do that like immediately. On my exam, on this question, you're going to get 2 out of 5 if you can do that. 2 out of 5. So you won't necessarily pass the test question if you can do the bare minimum, but it's really close. It was 15 degrees, right guys? Okay, so I'll give you guys 1 minute. Find Vx and Vy. So which formula for sine, cosine, tan did you guys use for Vy? Sine? Why'd you use sine? Because it's opposite to the 15 degrees? And Vx, you'd use which one? Cos, because it's adjacent to the 15. Okay, so sine of 15 would be Vy over 18. You can multiply both sides by 18. And that's Vy. For pretty much the exact same procedure for Vx, 18 cos 15 will get you Vx. Okay, so you can just jot down on your page those results to 2 significant digits, but you will have accuracy left over in your calculator. If you don't have a nice calculator, you might want to jot these down to like 3 or 4 decimal places. So mode, make sure I'm in degree mode. Yep. Okay, 18 sine 15. I got 4.7. Okay, and then Vx, 18 cos 15. I got 17.4. Okay. Yeah, it should be just 17. Yeah. I usually don't care about sig digs until my very final answer, but yeah, good. Degree mode. Okay. So we have just solved for the 2 components the moment it's fired. You see that? What are the x and y components the moment it's fired? Because as soon as it's fired, the acceleration due to gravity will act on the projectile, and this ball will come up, and this ball will come down. If I was to like draw a horizontal line to indicate the ground, then you can see it will follow this path. They call that path the shape. What would they call that path? In a math class, what they call it? P. Good. So you can call it parabolic, or the shape is a parabola. Either one of those is perfectly fine. If they're talking about some maximum height, where do we look for this maximum height? Good, right there in the middle there. Good. This is like some apex, maybe is a good word for that. The apex of the flight path. You could call this a dy. Why can you call that a dy? Yeah, it's a vertical displacement for sure. What are some key facts about the velocity of the projectile when it's at the apex? What is 0? The Vx or the Vy? Good. Vy equals 0 at the max. So she says, how do we know? I'll use my color green here. If this was the projectile, what do you know about the horizontal component? Does it change? So let's say that's the horizontal component. What would the horizontal component be over here on the right side? It would be the same. I've attempted to draw those the same. On the left side, which way does the velocity vector point for the y component? Up. And which way does it point on the other side? Down. So if on the left side of the symmetrical line in the middle, it's pointing up, and on the right side, it's pointing down. Somewhere in between, it would have had to be 0. Because if you're positive and then all of a sudden you're negative, somewhere you would have had to have been 0 in between, and that place is at the maximum. Think about something like this. You just throw something up in the air. At the very top of its path, it will momentarily have no velocity in the y direction. All right. So since you have a Vy of 0, it makes your life pretty good. If Vy is 0. Notice what's the one variable they didn't tell you anything about in this time. So time is this big fat question mark. If your time is a big fat question mark, which formula is a go-to formula? Yeah, the one that doesn't have it. Vf squared equals Vi squared plus a 2AD. Which variable are we trying to solve for? D. And that D is actually which type of D? A dy. I'm trying to solve for a dy. If I'm doing a dy, is the y component affected by gravity? So is it okay to have an acceleration formula acting on this? Right. But now I got to be careful. Which velocity vectors am I putting in here? It has to be the y only, because what do you know about the Vx? It's constant. So you have to put in Vy, this 4.7, into this formula. You cannot put in the 18, and you cannot put in the 17. It has to be the 4.7. Okay, so with Vf being 0, and Vi being the Viy, I can put in that 4.7. And the Viy is positive, not that it will affect it. But it's interesting because some people will make this mistake. What will they forget on this 9.81? The negative. It matters in this case because the initial velocity is positive. So it's shot upwards, but the gravity works downwards. The velocity's up, but the acceleration's down. That tells the formula that it's going to be slowing to a stop at the very maximum height, dy. Okay, so I'll give you guys a minute to solve this equation. Okay, so here we now have an arrow being fired at a 30-degree angle. This is the last one I'm going to do, so you'll have lots of time to practice. Okay, so I'll be around to help. Again, the initial speed is 25 meters per second. And like, before they even do anything, they just like, okay, find the x and y components. Find the x and y components. So you can do that for yourself. So that's the 25. The velocity that they give you, unless like otherwise stated, like explicitly, you're always being given the resultant, the hypotenuse. You're always being given that. That is the vector. Then we resolve the vector into its two components. So that would be the Vx, and this would be the Vy at 30 degrees to the horizontal. So go ahead and find those quickly. And after you've done last page, you should see that's quite quick. You should have a 25 cos 30 and a 25 sine 30. And using my tip 6506, and this one's 12.5. So look at the Vy. Look at the Vy. It's exactly half. What does that tell you sine 30 is? Sine 30 is half. That's one that, especially if you get to math 30, you'll memorize. Yep, the unit circle, yep. Okay, now this bullet right here, I'm going to put the use symmetry beside that bullet. This bullet, like maybe one or two of you guys would be able to come up with the answer to this one if I didn't explicitly teach you how. It's quite a nice little trick. So how long is it in the air for? Using symmetry, if you use this formula, A equals Vf minus Vi over T, rearrange for T, so you can go like this, Vf minus Vi over A. We know that A, the acceleration, is 9.81 meters per second squared down. Good. So this acceleration acts on the y component. So then which velocity vectors do I have to use? You have to be dimensionally aware. That acceleration only acts on the y component. So using symmetry and the fact that, well, let's switch colors here. The ball goes up and the ball goes down. And let's say right here, that's the Vyi. And that's the Vyf. So they're the same in magnitude, but opposite in direction. So same magnitude, opposite direction. And of course it has to be symmetric, so I would have like the ground. This is the ground. The initial vertical component is the same as the final vertical component in magnitude, but in opposite direction. That Vfy and Viy come from this guy right here. It's so important, I'll circle it twice. That's the vertical component, right? The 12.5. So now, when I go to use the 12.5, I'm super aware of everything in my life. Because I take physics and I come to class and I'm on time and I pay attention and I do my homework, I could solve for t. All right, what goes there? The Vfy, what goes in that first bracket? Negative 12.5. Why is it negative? Because it's headed down, and that's the way I drew the vector. And the Viy is positive 12.5. Now you have a negative 12.5, take away another 12.5, altogether that is, good, negative 25 over the negative 9.81. The two negatives cancel, and you get the 2.55. How many sig digs are we looking at? 2 sig digs? So 2.5 seconds. You did that differently. Okay, I'd love to look at it after. But sometimes you're we just talked about that for like a whole minute. It's the symmetry because the acceleration stays the same. So the acceleration's constant. So like on this side, the launch velocity, and then when it finishes, the final velocity, they're the same. They're the same magnitude, just in opposite direction. Yeah, because the gravity's the same. Okay, and that will give you, like this is the dx, and it'll find the time for the, I don't know, the journey or whatever, the ball path. Okay, so then it says how far does it travel? How far does it travel? So now they're looking for dx. Dx is just simply vxt. Why is it just simply vxt? Good, the horizontal component is uniform motion. Now for Vx, what do you use? The 21.6506. Where am I getting that from? Right here, right? Up here. Times the time, which I just found. It was like 2.5484. Multiply those together. I got 55. So that's it. Any questions before I show you the homework? Okay, so here we go. We're going to do these ones on Thursday, these challenge problems. This is the homework you're looking for. See how it starts at number 9? That means probably 1 to 8 was from Friday, I believe.